What's up, y'all? So I know this is a little weird because we're on chapter 7 in lecture, which is eigenvalues and stuff. But because we're teaching remotely, I wanted to give everyone an opportunity to come back and review material that I taught earlier in recitations, just as a way of reviewing for the final if you need to brush up on anything. And so with that, I just wanted to give a little bit of an introduction to chapter 2. So chapter 2, if you can remember that far back, was all about matrices. And so I just wanted to give, a little bit of a review of the motivation. You've seen hundreds of matrices so far this semester. You probably forgot why we even care about them, how we set them up, where they come from. So I just wanted to review that a little bit. So if you remember all the way back to Algebra 1 in middle or high school, you might be given something like this. 2x plus y is equal to 5 is one equation, and then x minus y is equal to 1 is your second equation. And you're tasked with maybe finding the set of solutions to this set of equations here. So this is a very simple set, so you may have already come up with the answer in your head. But if not, if you're thinking back to Algebra 1, how you would solve it then, there are a couple ways of solving it. The first of these is by substitution. And in this method, what you do is you want to isolate one of the variables here by solving for it in one equation and then plugging it into the other. So this is pretty elementary stuff. So you can say x is equal to y plus 1 if you rearrange the bottom equation. And then now you can plug that into the upper equation here. So you have 2x is now y plus 1 plus y is equal to 5. So that tells you that y must be equal to 1. Great. And what do you do with this? Well, now that you know y is equal to 1, you can figure out what x is. So you use this second equation here. X is going to be 1 plus 1, which is 2. And yep, this is math 240, but I did just write 1 plus 1 is 2. Anyway, your solution is 2 comma 1. Okay, so that's one way of doing it. Another way of doing it, which I really never used in Algebra 1 because I was scared of it, but you can add these two equations together. And so if you'll notice, I'll write them again. 2x plus y is equal to 5, and then x minus y is equal to 1. It's a little weird to think about, but if you add each of these terms together, the x's make 3x. The y's actually cancel, and then you're left with is equal to 6. So this tells you right off the bat that x has to be equal to 2. And then again, like substitution, you substitute this value 2 back into one of these equations, and you should find y is 1 as well. So again, we get the solution 2, 1, which is good for us because that's the exact same equation, or the exact same solution we got from substitution. Great, all is working out well. But you can see that this is a little bit tedious to do if you have, more than just two equations. So if I had 4 equations with 4 unknowns, it might take me a lot longer to do the substitution or the adding to figure out what my solutions to that set should be. So someone, probably got really frustrated with that and came up with a better idea. And the way we think of it is simply just recoding the information that we're given. So I'm going to take the same exact solution set as an example. So we have 2x plus y is equal to 5, and x minus y is equal to 1. Okay, so what we can do is we can kind of think of these equations as using the same variables, right? So then we're able to combine them into a form that's more appropriate to work with. So what I can say then is if I look at the x components of each equation, I end up multiplying, timeout, there we go. I ended up multiplying x in the first equation by 2, and then in the bottom equation by 1. Right? And then my top equation multiplies y by 1, and then my bottom one multiplies by -1, and then the top equation gives me 5, and the bottom equation gives me 1. So I've kind of written it in this really weird way. Hopefully you're listening to this with audio, else this is just not going to make any sense. But then what we can do is we can just treat these as little column vectors here, like this, and also here. So then pretty much what I've said then is that I I've encoded it in the way such that I can read off my system of equations like this. So 2x plus y is equal to 5. And then my second equation, x minus y is equal to 1. So again, all I've done is write it in a more easy to work with form. And then what we can do with this is we can take these two column vectors here that we have, and we can put them in a 2 by 2 matrix like this. 2, 1, 1, negative 1. So we get this 2 by 2 matrix, and then we'll talk about this in a second. We put x and y here as the 2 by 2 matrix you're going to multiply to get the column vector 5, 1. Sorry, this is 2 by 1 x and y vector here. Okay, so if we look at this then, the way we figure out what this actually is equal to, we use the rules of matrix multiplication, which you may not have seen before if you're watching this for the first time. But pretty much we take this 2 here and we multiply it by this x. And then we add that to this 1 here multiplied by this y. So if we read this out, we get 2x plus y, and then you expect that to give you, I'll use yellow, I guess, what's up here. So you get is equal to 5. Great. So again, then you take this 1, you multiply by the x, so you get x. You take this negative 1 here, you multiply it by the y to get minus y, and you should get what's on the bottom here is equal to 1. So you'll see that all we've done is just input our information that they give us in the problem into a way that's a little more simple to work with. And you might say, how is that any more simple to work with? It looks very complicated, and I don't really want to be working with matrices if I don't have to. The reason being, again, if we get 4 by 4, 5 by 5 variables here, as we'll see in a second, these matrices will actually give you a more streamlined process to figure out what your solutions are. So let's go ahead and actually see what we would do next in the problem. So let's go back. I'll rewrite the matrix here. 2, 1, 1, minus 1 multiplied by xy is 5, 1. Okay, so what do you do from here? You have to form what's called an augmented matrix, and you'll get very good at doing this. It's just formality, I guess. What you do is you take the matrix you're given, 2, 1, 1, minus 1, that's all the coefficients from your equation on the left-hand side. You draw this vertical line here just to keep you organized pretty much. And then you write the values you are, not the ones you're solving for, the ones you care about on the right-hand side of your equation here. So this is forming the augmented matrix for the system. And then by forming this, you're actually able to solve the system of equations here. And so the way you do that, you have 3 possible operations you can conduct on this augmented matrix to help you get a little more, or an easier matrix to work with pretty much. So the first of those is you can permute 2 rows. All that means is you switch the order. So for instance, if you want this row here to instead go up here, you're allowed to do that. You can switch them. The important thing is you take these values on the right-hand side of the bar with you as well when you do that. You're allowed to add 2 rows, add or subtract, same thing. And then lastly, you can multiply a row by some number as long as it's not 0, by a non-zero scalar. Okay, so the textbook gives you these 3 things you can do, but why do you want to do these in the first place? What's your end goal here? So you want to transform this matrix here that you've written into something that's easier to work with. So again, if you just remember that everything in this part, whoops, this is my first time using an iPad, so I'm gonna take some getting used to. Let's use green, why not? If you remember what this information in this matrix actually coincides to, it's the coefficients of your system of equations on the left-hand side. So pretty much what we want to do is we want to get those coefficients to be as simple as possible, so we don't have to do any division, we don't have to do any substitution, right? So ideally, we should be able to get this down into this form here. And then there will be some stuff over here that results from you adding these 5s and these 1s together. But this is our end goal. We want to get into something that looks like this. Now there's a distinction between having a 0 here and not having a 0 there. We'll talk about that in a little bit, but for the most part, we just have to take these 3 operations here with the goal in mind that we just want to simplify our matrix that I circled in green. All right. So let's go ahead and do that then. So we start with 2, 1, 1, negative 1, 5, 1. And so the first thing I want to do then, if you look back over here, I'll try to get rid of this. Great. We want to get a 1 in this place here. So you'll note there's one thing you can do. You can divide that entire row by 2, which is the same as multiplying by a half. We're allowed to do that. But then you end up with fractions in the top row, and that's going to make your algebra a little tricky from then on. And I myself like to avoid fractions, so what I'm going to do instead is I'm just going to move the bottom row to be the top row. So I have 1, negative 1, 1, and then I move the top row to be the bottom row, 2, 1, and 5. So that's totally allowed. It's one of the 3 things we're allowed to do. Great. And then this squiggly line here that I drew just means that I've performed a row operation. And it's just, a good habit to get into writing underneath it, this little squiggly line, what row operation you actually did. It's easier for graders. It helps you go back and check mistakes. So what I do is I just say, I keep selecting eraser by accident, P for permute, and then 1 and 2 to let you know that I switched my first and my second row. Okay, great. So I got the 1 there. The next thing I need to do is get a 0 in this place here. So this 2 has to go. Really the only way I can get rid of that 2 is if I add some rows to the other. In this case, I need to take 2 times my first row and subtract it off my second row. So I'll go ahead and write that before we do it. I'm going to take my second row here, and I'm going to make it what it currently was, or what it was, subtract off 2 times row 1. So my first row, nothing happens to it. And then this 2 here becomes a 0 because 2 minus 2 times 1 is 0. 1 minus 2 times negative 1 gives me a positive 3. And then 1 minus 2 times 1 gives me, again, a positive 3. Great. Okay, and then lastly, what we need to do is we need to get, I'll use a different color. We need to get a 0, or not a 0, sorry, a 1 in this spot here. And so what we're going to do now then is just obviously divide that last row by 3 to get this equation here. And to write that out, I say row 2 is a third times row 2. Great. So I'm going to pause here and just let you think about why it's okay that I'm going to stop. So I could, get rid of this negative 1 up here. I can easily do that. But as you get, bigger and bigger matrices, sometimes it's not actually necessary to go through and get zeros above the diagonal. So in this case, it's going to be sufficient for me to say, okay, I'm done. I'm just going to read off my system of equations now. So remember for the last time that this matrix here actually corresponds to just the coefficients. And so this first column here corresponds to the coefficients of x, and the second column corresponds to the coefficients of y, right? So I can just read out what this equation gives me if I were to go back and uncode this matrix into the formulas. So I have x minus y is equal to 1, and then 0x plus y is equal to 1 as well. I just wrote the 0 there to keep you oriented with what we're doing. And so you can see now I can easily read off my solutions. This bottom row tells me y is equal to 1 simply. And then this top row, if I know that y is equal to 1, tells me that x has to be equal to 2. So then we get the solution 2, 1 by doing these row operations to this matrix. So what we did here, we used what's called back solving. So what I did is I said, okay, I have zeros below the diagonal, and I have ones along the diagonal. That's good enough for me. I don't really need to do any more steps because I know I can go back and I can write out my equations here, and I'll be able to find my solution that way. So that's what we just did here. This is back solving. What you can also do is you can find what's called the reduced row. Here, I'll put a 1 here. You can find the reduced row echelon form. So that's similar to what we were doing here, but instead I actually need to go all the way and I need to get it in this form here. So that right here, when you have only ones along a diagonal and zeros everywhere else, is called reduced row echelon form. And we'll see why that's actually advantageous to use sometimes. So let's go all the way to the end. This matrix I had here, which I said was good enough. 1, 1, and let's put it in reduced row echelon form. So let's go one more step. Let's get rid of this -1 right here. Let's make it a 0. So to do that, I'm just going to add the bottom row to the top row. So row 1 becomes row 1 plus row 2. So I get 1, -1 plus 1 is 0. 1 plus 1 is 2. And then I have 0, 1, and 1. Okay. So I took one more step, and now let's actually read off our system of equations that's encoded with this matrix here. So I can read this out. The first line reads x plus 0y is equal to 2, and the second one reads 0x plus y is equal to 1, and obviously this tells me exactly x is 2 and y is 1, but look how little work I had to do once I got it into this form. So the advantage of getting it into reduced row echelon form is you can literally read off the solution to your equation from this column here. But sometimes it's a lot more work, and sometimes it's actually easier for you to use back solving instead. So that's just a little bit of a review of encoding matrices. We'll get back next section with how we use them, and we'll talk a little bit more about inverses too.